thanks for watching my presentation video. I am Byung-jun Kim from Team 15. Today I will present our Alpha project on visual solving for pack-in hold tags, especially robust machine vision technology-based TCP position control for bolt testing of low battery pack in electronic vehicles. Okay, our project overview. To develop a robust automated system for recognizing and testing boards on EV low battery packs using advanced machine vision and robotic control. Core technologies are deep learning and TCP control. Our system architecture. There are vision processor communicate with NUC and the NUC control the control system. This integrated framework is decoupled modules. Vision and control systems operate independently to maximize performance. It's like computational efficiency. They are integrated in ROS2. Our technical challenges are in two domains. Vision challenges, illumination variance. Traditional edge-based algorithms fail in low light or backlight conditions. This cause also vanishing gradient problem. Precision requirement also was very important. Control challenges was complex kinematics. Controlling nonlinear movements of 7DOF multiple joint lobe structure is computationally intensive. So we make the solutions with several constraints. Okay, let's see visual perception. There are a lot of methods. Classical CV, Glahe, Kenny, Lensa, etc. Deep learning based methods, CNN, object detection models like SSD or VIT, etc. These are sample of these models. Why we chose the deep learning based method? To solve the illumination variance, we chose a deep learning approach. Classical algorithms have the limit to solve illumination invariance because often they use pixel gradient which can't use in these situations. Saturations lose the and texture of pixels. A lack of contrast, the edges are obscured by shadows. But the deep learning methods, they have potential for solve these problems, so we chose the deep learning method. For model training, we established a rigorous data pipeline. We utilized our Chromacos to acquire precise 60-post data, serving as the ground truth. Furthermore, we implemented an auto-annotation system to generate semantic masks and bounding buses, ensuring the dataset covers the stochastic environments, and within the data augmentation, we can train the model that would be more robust. There's our dataset examples. Now, I will explain our control logic. We adopt a decomposition strategy, splitting the problem into a 2D plane alignment phase, followed by a 3D vertical insertion phase. To solve the inverse kinematics for the 7D of lobe, we moved away from iterative numerical methods like Newton lesson, which are computationally expensive and prone to local minima. Instead, we developed an analytic solver that derives a closed-form solution. Crucially, to resolve the redundancy, we applied a geometric constraint on the wing pin rotation angle. By setting Q3 equals to minus Q4, or a specific coupling ratio, we constrained the infinite solution space to a single optimal solution, ensuring the manipulator avoids collisions with the battery pack. Our system operates on look and move visual solving strategy. The control loop functions as follows. Acquire vision, the camera captures the low image, target joint angles. Motion command, the lobe moves towards the target by a fixed ratio, little than a full step to ensure safety. This process iterates until the error between the current state and the target state falls within a predefined threshold. Here's our operate video. Here's our 3D pose of hole, and the robot vision recognize this 3D pose and robot move to this point. Okay. Overall, our system architecture detailed. Conclusion: we established basic Visual Server framework and made the dataset for future work. For future work, we aim to implement efficient fine-tuning using large-scale pre-trained models like YOLO V8. Additionally, we plan to design a lightweight adapter to efficient fine-tuning. Actually, we have a lot of errors, and in the future work, we have to reduce the errors and optimize control algorithms and vision process for embedded systems. Thank you for your attention.